Hello again, and for this next lecture now we're going to talk about the second part of the immune system. In the first part I really did a very brief introduction, staying at the surface of definition mostly. But now for the second part we're going to try to dig a little bit more into mechanistic processes and really the immune response. So we'll talk about antibodies and how antibodies are going to be able to recognize some antigens, and we'll talk about the process of two different types of the immune system, the innate immune system and the acquired immune system. So we'll talk about vaccination, and we'll talk about the role of the different cells in those two innate and acquired immune systems. So let's start together. And the first thing I would like to define is the term immunity. This is obviously something you know, and you've heard before, the term immunity. But I want you to also make sure you understand the specificity of the idea of the immunity. So it means that you are protected from a disease. And the word disease is important. It means that you are not really protected against infection. You are protected against disease, which means you can be infected, but the infection is not going to develop into a disease. It's a very important field in pathology and in medicine in general. The reason why is because if you think about it, there's really no other system in our body that allows you to heal or to defend against a disease. And also there's no drugs, there's almost no drugs on the market that are really getting rid of a disease or allows you to be cured from a disease. And most of the drugs we are using are actually helping your immune system. Helping the immune system to either get stronger or trying to weaken the bacteria so the immune system can get rid of them, for example. So there's very, very few drugs on the market that are actually really working on the cause of a disease and can really cure you. You can think about maybe chemotherapy for cancer or maybe the antibiotics for bacteria, but most of them are actually helping the immune system. So what's the system that our immune system is going to be able to use against a virus or against an infection? There are two commonly described systems: the innate immunity, and that's the one you are born with. As soon as you're born, you have actually, fortunately, we have an immune system that can defend us against basic bacteria and infection. The second one is called the adaptive immunity or acquired immunity, and this one is obviously going to be built up along your life, and mostly as a kid, a young adult. So among the two, innate and adaptive immunity, if I had to say that one of them is more important than the other, I would say the adaptive. And you understand why later. The adaptive immunity is going to allow you to, like the name, adapt to the place you are, adapt to the people around you, and that's going to be the strongest, the most flexible system. The innate immunity is obviously very important. We'll see that in the second part of the chapter. We'll see that when people have genetic, or kids have genetic problems in affecting their innate immunity, that creates a lot of different problems. Even some kids can't survive depending on the problems. So both are important, but the adaptive immunity might be the most important for me. So let's start first with the innate immunity, and I'm just gonna mention the system, the most important cells who are involved in this innate immunity. And again, this is the immunity that you are born with. So what are we born with that allow us to protect against a disease? The first one is a physical barrier. So epithelial cells and epithelial barriers, we've talked about those epithelial cells before in the respiratory system, if you remember well. I talk about them in the squamous cell carcinoma, for example. So those are physical barrier, and you can see here on this graph that is blocking infection, the entry of those infectious agents. So they are key, they are very important. They are the first in line, actually, against this, against infection. Other cells are important also. We are born with phagocytosis cells. Cells who are responsible for phagocytosis, and macrophage neutrophils are the family of those phagocytosis cells that are able to grab and digest. They are already set up, if you want, when you are born, to be able to do that. So they are key, actually, especially to understand the beginning of the immune system. We'll see that later. The next category of cells are NK cells. NK for natural killer. A natural killer, and then like their name, natural killer, means that they are active right away. They don't really need to be turned on, if you want. They are on all the time, and they will be able to be, they are powerful, and they will be able to digest antigens. The problem with the natural killer cells is they are not super clever. Once they are active, and when they are active, they can't really adapt much, and whatever they're gonna encounter, they're gonna try to kill it, and that's it. So useful, but not so useful at the end when you consider the entire immune system. The last system I want to talk about is the complement system here. The complement system is a little bit outside, I would say, of the immune system. I mean, not really of the immune system, but outside of the innate immunity, even outside of the acquired immunity. Like the name, it complements. It's a complement system. It's made out of proteins, a bunch of proteins, 10 or 12 of them. And it's one of the most powerful systems we have, actually, maybe the most powerful in the innate immunity. And it requires, anyway, both the innate immunity and the adaptive immunity to be able to be stimulated and to be able to be active. So it's not completely independent, but it's kind of an independent system because it's made of proteins and not cells, like the natural killer cells, the epithelial cells, the phagocytosis cells. So it's a different system that we'll describe at the end of this lecture. Okay, even though there's a few of those cells for the innate immunity, actually the system is quite complex when you take everything into consideration. But for the adaptive immunity that we're going to talk about now, the system is more complex, and it's logical because it's the system that allows you to recognize over time different type of pathogens and allergens, and will adapt to it. So to be able to do that, you need to have different systems. You need the recognition systems, you need to have communication between the cells, you need to have different level of cells that can kill, like wire cells that can fight and kill, and you need different level of fight also. You need to have you can fight from a distance, or you can be directly in contact and physical contact. So there's many different systems in this adaptive immunity. I'm gonna try to be as simple as possible, but giving you also the right information. And enough, at least, for us to understand the disease we'll talk about later. So you need to pay particular attention to this next few slides because they are important. In the adaptive immunity, there's two categories of system that are complementary. They are not opposite, they are really complementary. The first one is called the humoral system. Yeah, and that's the first one we're going to talk about. And then the second one is called the cell-mediated system that we'll talk about later. So the humoral system is mediated by B cells. Okay, we didn't really talk about T and B cells, T and B lymphocytes, but they are part of your white blood cells. And B cells are very important in the acquired immunity because they're responsible for the humoral system. So you have the schema here. Look at the right part of the slide here, humoral immunity. The B cells here have a very important role of being able to recognize an antigen. So the antigen is going to bind to it, and they're going to, we'll see later on how, but they're going to be able to recognize this antigen. And then, because of that, they're going to be activated by it, and they mature into a plasma cell. And that's an important idea. Okay, it's B cells and plasma cells are actually the same, except that the plasma cells are mature B cells. We usually say it's a mature B cells. It's mature because to have a plasma cells, you need to activate the beta cells first, or the B cells first. Once the B cells become plasma cells, they are actually able to produce a very important part of the acquired immunity is called antibodies. So I don't know if you heard about antibodies before. We're going to describe their role right away after, but antibodies are usually represented like Ys, like this. You see the Y on the slide, and there's a reason for that, because they have a membrane part. They can stick to a membrane, and they have a recognition site close to it. Or you see here, for example, a complex antibody antigen with the antigen then binds to an antibody. So what are those antibodies? Why are those antibodies important? When B cells mature into plasma cells and produce antibodies, then those antibodies have a whole array of role and capacity and function. One of the first is here to bind to the antigen, like I said before. Yeah, so binding to the antigen to form a complex. Why is that important? Because they're going to be able to recognize that once an antigen binds to an antibody, then we have, as the immune system has a way to recognize this antibody and say, oh, okay, this antibody is activated, so there's something going on, and I need to put things in place to fight this antigen, for example. But that's not the only role of antibodies. Antibodies are by themselves also able to fight and get rid actually of some of the antigens. So they can agglutinate, have an agglutination idea, so clumping of cells, and by doing this, they can agglutinate cells, they can neutralize cells, they can also neutralize bacterial toxins. They stick to it, and they form like a glue around the toxin and the cells, and then the cells can release other toxin, or the toxin can reach other cell type. So that's a very important aspect of the antibodies. Another role is called lysis, and lysis is really a destruction of the pathogen. The way the antibodies are doing this is they are making holes on the envelope of this pathogen, like a bacteria, for example. So they're going to make holes, and then those bacteria are now going to be exposed to other cells, and mostly it's going to change the pH of the bacteria, and by doing this you neutralize usually the enzymes and the toxins that those bacteria can release. Other roles are adherence to effector cells, facilitation of phagocytosis cells. We'll see those different roles later on, but those 6 roles, binding to an antigen, agglutination, neutralization, lysis, adherence, and facilitation, are the well-established role of antibodies. Okay, so it's not coming from me, obviously. It's classic. If you take any pathophysiology book, or if you take any book on disease, then and describing the role of the antibodies, you'll find those 6 roles. Okay, so those are really important roles and really well-established roles. So I said that binding to an antigen is one of the most important role of antibodies, and it's not as simple as just one antibody binding to one antigen. Consider an antigen as a bacteria, okay, in our case, so that would be easier, maybe to more concrete for you to understand. So here I'm gonna explain an important concept of the epitope here, epitopes. So epitopes are what you see here on this graph. So in green, okay, this is an antigen, this is a bacteria, and on every one of those, let me erase that so you can see better. On every one of the spiky part of the antigen, you see here there is a different type of shape. Here, for example, is kind of a triangle, sharp, and this one is more like a square end, and this one is more like a round end. So that's what we call an epitope, and it's kind of a different ends of an antigen, and it's important for an antibody to understand that, because if the antibody wants to be able to recognize an antigen, it's going to have to recognize all of those. Okay, so on this graph is an antibody A, B, and C. You're going to need three, in this particular example, you're going to need three different kind of antibody. You see this one here that can stick to the round one, this one here that can bind to the square one, and this one here that can bind to the triangle one. So A, B, and C. And it's only when those three different type of antibodies are going to be produced and bind to the antigen that you can neutralize the antigen. If you want, the epitope is the ID, is the identity of the antigen, to be able to recognize the shape and recognize what the antigen is. It's like a driver license, but in that case, you would have three different type of driver license. And you have antigen that have 2, 3, 4, 5 different type of driver license. Okay? So 3 is just an example. Some of them are even more complex than 3. They can have 5, 6 different type of epitope. So it's like if you really want to have the information and know the information on somebody, you will need to have 5 or 6 different type of driver license. So concretely, in terms of disease, in terms of pathology, why is that important? It's important because let's say you're going to be affected, you're going to be infected the first time with this particular antigen, this particular bacteria here. Okay? And the first time you're going to be affected, your immune system, the B cells are going to mature into beta cells, into plasma cells, and they are not going to have time, they're not going to be able to produce an antibody against this antigen. So you're going to get sick. And you're going to get sick quickly, and then the symptoms are going to be severe, and then it's going to take some time for you to recover. The second time you are exposed to the same antigen, this time the immune system was able to see it before. He's going to be able to recognize this antigen, and he's going to be able to produce one antibody. This particular antibody, for example, the antibody A. So it's going to be able to bind to this particular epitope. Because of that, you're still going to get sick because you didn't recognize all three, but the symptoms are not going to be as much because you're going to be able to neutralize some aspect of this antigen, and you're going to be able to recover faster. The third time, fourth time you are exposed to the same antigen. Now this time the immune system is clever, is going to recognize all of those, and you're going to be able to produce antibodies A, B, and C binding to those three different type of epitopes. So this time you can neutralize completely the antigen. So you're not even going to get sick. That's the idea. It's what we call the immunity. You can be infected. There's nothing you can do against an infection. If you are breathing and there is an airborne infection, you'll get it into your lungs. But because of this acquired system, now you understand the idea of an acquired system. you've been exposed to this one a couple of times. The immune system can recognize it, produce antibody A, B, and C, neutralize it, and you don't even have the symptom. You are still actually not sick. That's why it's so important to understand the idea of the epitope. It's because it has a physiological consequences and a pathological consequences. You can really understand the role of those antibodies. That's why I prefer to focus on this binding role for the antibodies because I think it's a good example for you to understand the role. Okay, so that's important. Really make sure you understand epitope. Make sure you understand why you need to produce different type of antibodies to recognize this different ID, and understand also that once you are doing it, you have all the antibodies you need, then you are immune to this particular antibody. To be a little bit more complete on that idea, it's again not as simple because those antigens can actually adapt also. And once they do that, they can actually mutate those epitopes. So it's not something that is like a concrete stage or status for this antigen. The antigen, especially bacteria, can actually mutate those epitopes, and you're going to have to adapt again and produce different type of antibodies and get sick again and so on. So it's more complex than we can think of. So this is good. Okay, this is the normal function of antibodies, and once they can recognize all of those epitope, then it's good. You are immune to it. With the immune system, there's always another side of the coin, if I can say that this way. We always define the immune system as a double edge. And it's a double-edged sword because there's always a positive, and then this positive can turn into a negative. So let me give you an example here. That we were just talking about a recognition of an antigen. So sometimes we can be infected or we can be exposed to antigen or substances. In that case, the example I'm going to give you is the example of penicillin. Penicillin is a very small molecule. It's so small that your immune system can even see it. It can even recognize it. So you are exposed to penicillin. You have an injection of penicillin, for example, and you know penicillin is an antibiotic. It was the first antibiotics, and it's such a small molecule that you don't react to it. And then penicillin is going to do his job at trying to destroy the cell wall of bacteria. But for some reason, in some people, this very small molecule is going to be recognized by the B cells as a foreign substance. And the B cell is going to produce antibodies, and those antibodies are going to do their job, and they're going to go and bind to penicillin. Okay, so in that case, we call the small molecule aptens. Okay, so aptens are small molecules that cannot produce an immune reaction. Okay, they are too small to produce an immune reaction, and the antibodies can, in that case, be carriers, and they can bind to an apten. But the problem with this apten carrier complex now is that it's becoming bigger. And it's becoming big enough for the immune system to see it and to take this as a threat. And now the immune system is going to overreact to it and say, oh, I need to get rid of this. That's an example of an allergic reaction to penicillin. And actually, it's a pretty common allergy. And the allergic reaction of penicillin can actually be pretty virulent, pretty severe. So you see the double-edged idea that I was telling before. It's a very good system when the antibody is recognizing this antigen, and then they can get rid of it. But it's also a bad system because sometimes it's recognizing things that is not supposed to recognize, and it's creating a problem with the immune system and creates, in that case, an allergic reaction. Okay. So this is the basic of the acquired system. Okay, so this slide is also important. It's telling you the role of those B cells, and actually by doing this, we're also going to talk about vaccination. So you see here, let's just follow this graph because I think it's easier to just follow the graph than the text. So you have B cells, okay, and the first time you're exposed to an antigen, let's say it's the flu, okay, so you're exposed to the flu, the virus, and the B cells are completely naive about this virus. They never see that before, okay, so that's why we call that naive B cells. Naive B cells are exposed to this virus, and then because they're completely naive, they don't exactly know what's going on, and it's going to take time for them to be able to be activated and produce antibodies. The curves you see here in green is actually the amount of antibodies that a B cell is able to produce. And so you see here it's going to take some time for the activated B cell to produce antibodies, and the amount of antibodies that the B cell is producing is not so much. Because of that, you're getting really sick. You get all the symptoms, and it's difficult to recover. Then you recover from it, and within weeks or months, you are exposed to the flu again, the same virus again. But in that case, the system is clever, basically, and rather than get rid of all the activated B cells, there's actually some activated B cells that are going to stay around. And in that case, we call them memory B cells. So memory B cells are actually activated B cells that are keeping the memory of the antigen. Okay, so they're not naive anymore, they are now memory B cells. And because they have the memory of it, they know it, they understand it, they can react much faster to it and much stronger. So you see the level of antibodies that those memory B cells are able to produce is much more than the first time, which means you might even be immune to the flu. You might actually not develop the symptoms, and you might not actually be sick. Okay? So you understand this step by step from the naive B cells that are exposed for the first time here. This is the first time, and here is a second time when they are exposed to the same antigen. And then they develop a memory, there's a memory of the system, and then the immunity is developed. How long can we keep those memory B cells? Actually, it depends on what's the antigen. Actually, there are some of those antigens where you keep the memory B cell for your whole life. You are exposed one time or two times, and then you have those memory B cells for your whole life. Sometimes those memory B cells are going to stay only a year, sometimes 5 years, sometimes 10 years. So that's the idea of the vaccination. When you are vaccinated, you have this part of an antigen that is injected, and then you create memory B cells. And then the next time, if the real thing is coming, if you have the real antigen coming, then you have this immunity buildup. Okay, so that's the idea of the vaccination, and that's also the idea of a booster. That's why sometimes you need a booster after a year, or sometimes you need a booster after 5 years, or after 10 years. So you have the example here for the tetanus, for example, where you need a booster every 10 years also. Okay, so this is an important concept because it's really underlying the whole function of the acquired immune system. And I told you before, the acquired immune system is certainly the most important, and now you can understand why. Because it allows you to be immune, so not to develop diseases to things you have been exposed already before. So that's an important system. Okay, I told you before there's two different types of acquired immune systems. So you could actually understand that this way. we said acquired, and on one side there is humoral, and on the other side, that's what we're going to talk about now, is the cell mediated. Okay, cell mediated, and here you have acquired and you have innate. So when you study, you can actually make this graphically, and then you can put here all the explanation we talk about for B cells, for example, and here all the explanation we're going to talk about for T cells. Okay, so it's up to you. Obviously, you can study, but I like when I study, when I try to understand things, I like visual, and I like to put that into a perspective. So let me remove that. It will be more clear after. And now we're going to talk about the cell-mediated immunity. So cell-mediated, like the name, means that it's directly mediated. There's directly it's cells that are directly in contact with the antigen. We see that before I was talking about B cells producing antibodies, and then the antibodies were going to bind to an antigen. So the B cells were not directly in contact with the virus or the bacteria. For the cell-mediated immunity, that's the case. The cells, and in that case the T cells, okay, the T lymphocytes, are going to be directly in contact with the antigen because they are cytotoxic cells. They have enzymes, they have proteins, they have toxins that they can use to actually destroy a bacteria or a virus. So they are maybe the most powerful system we have because they can physically go and get rid of the virus. So it's really an important system. And I want you also to keep in mind that it's not because I presented things in a sequence. So from adapted immunity to humoral and now to cell-mediated, that's how it works for the immune system. Actually, when you are sick and you are exposed to something and you're infected, both the humoral and the cell-mediated are active together, and they will, in different ways, going to fight together. Okay, so it's a complementary system. It's not as a sequence, but they run in parallel. And the innate immunity too. Okay, I also didn't say that, but all the phagocytosis cells, the natural killer cells, everything will be on if you are sick. So what's important for the T cells to be able to go physically and get rid and kill antigens? There are a couple of things. The first one, and I put it here, they need to recognize those cells. And I'm going to show you later on how they can recognize that. It's actually here on the graph. If you look at the right of the cell, of the slide, it says MHC. Okay, so we'll talk about this MHC system later, but that's the recognition system. That's how a T cell is able to recognize what they need to destroy. Otherwise, they would destroy anything that would be in front of them. Okay, so they need a system to be able to recognize what they need to destroy. So that's one. And the second thing is, obviously, they are not directly in contact with an antigen right away. They're going to have to chase this antigen. They're going to have to find a way to follow this antigen wherever this antigen is going to go and be able to destroy it. So I'll describe that later on. Okay, so it's called chemotaxis. So this is the lymphocytes, okay, the T lymphocyte system, the cell-mediated system. And in that case, because we said that we need to have a recognition system, it's also where you have two different types of cells. You have regulatory cells, the ones that are able to organize the system, and we call them helper. Okay, so helper T cells, CD cells, okay, CD4 plus CD cells. I'm mentioning that now because we will talk about the CD cells later, CD4 helper cells. So you can hear about it now. So the regulatory system, okay, called regulatory cells. Regulatory cells are not going to be able to fight. they're not going to go and destroy a bacterium. The one that can do that are the effector cells. Okay, that's why we call them effector cells. It's mostly the T lymphocytes. Okay, T cells. The T cells are the one that can effectively get rid of an infection in the bacteria. So here there's an important idea. There's an important idea behind those different type of cells that you need to understand. And this is the idea of the pluripotent stem cells. So maybe you've heard about stem cell before. It's because it's a hot topic in research, and it's a hot topic in medicine now. Stem cells are those cells that can differentiate into any type of cells. So we have stem cells, and we could differentiate those stem cells into liver cells, or we can, if we need, we can differentiate them into nerve cells or skin cells or whatever other cells we need. Okay, so those are stem cells. And obviously they might be revolutionary for the treatment and for a lot of diseases. Pluripotent stem cells are different than stem cells. Pluripotent stem cells are actually already differentiated into one category of cell. Yeah, so pluripotent stem cells, in our case here, the one coming from the bone marrow, are already differentiated into lymphocytes, if you want. Okay, so they will be maturing, they will be transforming into a white blood cells. They can't be a liver cell or a nerve cell. They will be a immune cell. And in that case, they can be either B cells or plasma cells, like we mentioned before, or they can also differentiate into a T cell. Here, there's a big player. Here, if you look at the graph, there is the thymus. We've talked about the thymus for the endocrine system, if you remember, and producing enzymes like T3 and T4. That's why we call them T. That will help the lymphocyte stem cells to differentiate into T cells. Okay, so that's a link between the endocrine system and the immune system. There's many, that's really, if you really want to understand the immune system, you also need to understand the crosstalk with the endocrine system. So what's important here, the bottom line and the take-home message is that T cells and B cells are actually coming from the same stem cells, and depending on the situation, if you need more B cells or if you need more T cells, then the endocrine system kicks in and produce enzymes that allows this different type of cells, the differentiation of the cells. In general, we have around 60 to 70% of our white blood cells that are T cells, and around 20 to 30%, maybe, or 20 to 40%, depending on the situation, of B cells. Other cells that we've talked about are natural killer cells. Again, we've talked about this before, so I'm not going to spend too much time on this. I want to spend a little bit more time on this particular graph, or on this particular idea. So this graph is important, and I'm always trying to make sure you pay attention and make sure you focus on what's important during lectures. So this graph, for example, is important. It's important because it's kind of a summary of the two innate immunity and mostly the acquired immunity. It's a summary mostly of the acquired immunity. And not only it's a summary of that, but we're also going to introduce a new category of cells that we didn't talk about before, which are the APC cells, or antigen presenting cells. Okay, so APC, antigen presenting cells. Okay, so let's start. Now we're going to start from the top. So you see here what the red arrow is. Those antigen presenting cells, or APC cells, are macrophages, or the family of macrophages. Yeah, so there we have very different type of macrophages from different type of organs. For example, macrophages in the brain is called the glia cells. macrophages on the skin, is Langerhans cells, and so on. So macrophages are able to phagocyte, okay, so they can engulf a virus and they can digest this virus. And that's the way I presented them at the beginning when I just talked about phagocytosis and macrophages. Okay, so they can do that, and you see it here. And you see a virus in green, and like green cylinders here, like green diamonds, and the APC cell is going to grab it and engulf it and digest it. Okay, so you see all the small pieces here that are going to be digested by powerful enzymes inside the APC cells. But they are called antigen presenting cells. Antigen presenting cells. They can present the antigen. How do they do that? So they are clever to be able to digest what's harmful from a virus, for example, but to keep an important part of this antigen is the epitope. Okay? You remember a few minutes ago I introduced you to the idea of the epitope as the ID of an antigen. So you see here they digest everything inside the macrophage, but they keep these little triangles. They keep the epitopes, and then once they recognize that's the epitopes, they're going to be able to push those epitopes on the surface of their membrane. They're going to push this out and basically present this to the rest of the immune system. Why would they do that? It's because they just want to tell others that now be careful, we've been infected by this particular virus, and here is the ID. If you see this particular virus, then you need to react and you need to attack, you need to destroy it. Okay, so it's really like this most wanted gangsters that you can see in the old movies, for example, and you see, oh, this is the ID, this is the face, this is the name, and if you see it next time, catch it or kill it, and you get rewarded. This is the same idea. They're gonna be able to grab and to push those epitope as the ID of the system, of those antigens, and present it to the rest of the system. Okay, so that's the idea why we call them antigen presenting cells. They can be considered as the first line of the acquired system because they are the one that can recognize antigen. Who is going to recognize that and get this information? It's actually the regulatory system, the regulator cells, and the T helper cells. Do you remember? We've talked about those T helper cells quickly. The T helper cells and the CD4 cells, okay, CD4 plus cells, which are one category of T helper cells, but those are maybe the most important. They are central in the system. You see here they are making the link between the presenting system, the APC cells, and the rest of the acquired system, the humoral and the cell-mediated system. So now, once the T helper cells have been able to recognize this epitope here, they are activated, and they can start to send signal to the B cells, and they can start to send signal to the T cells to be activated and fight. And they will fight with different systems, like we mentioned before. B cells are going to become either memory cells for the memory system, mature into plasma cells and produce antibodies for the humoral system. Yeah, so you could actually understand that this way. This is the humoral system. It's not easy to write on this screen. Humoral system, and here is the cell mediated system, and overall this is the acquired. So you could add the acquired immunity. You could add that to the graph if you want to when you study. So you see the the T helper cells, something I didn't mention before, how do they communicate with the others is by producing cytokines. And we've talked about the cytokines, those proteins that are able to communicate and bring other cells in. Okay, so that's really the idea of cytokines. They communicate, so different type of cytokines will communicate with B cells, other type of cytokines will communicate with T cells, and that's how they can specifically activate the system. You can look at this YouTube video also. It's a pretty cool video that explains the T cells and the B cells and the system overall. So let's just go back to here. This is a little bit crowded now, but let's just focus on the top here. There's something I didn't mention yet. How do those AP cells are going to be able to recognize those viruses and those epitopes and produce these epitopes? It's the MHC system, and we've talked about this MHC system also here. If you look at the bottom with the T cells, and I said this is the recognition system. So MHC stands for Major Histocompatibility Complex. Histo, okay, so histo is cells, and compatibility obviously is to be compatible, so with a recognition system. MHC system. There are two different types. We call that the correct cell-to-cell interaction. I forgot to say that. It's the cell-to-cell interaction. So when you say correct cell-to-cell interaction, is basically for the immune system to recognize what's part of me, what's part of my immune system, and what is a foreign system. Recognizing viruses and recognizing bacteria. There are two classes. The class 1, MHC class 1, is the one that we can recognize inside of our own cells. So intracellular signaling, intracellular recognition system. Why do we need a intracellular or inside recognition system? Basically, if you think about a virus, and the virus would be able to penetrate inside of the cell, and then if it's inside, and we don't have a system to recognize what's foreign inside of our cells, then we're done. The virus is never going to be able to, we're never going to be able to get rid of this virus. So we have this class 1 is inside of our cells. And obviously the class 2 is the one we were talking about for the APC cells, the one we're talking about the T cells, the one with the helper T cells, the one that is at the surface of the cells on the membrane. So the ones who are directly in contact with the antigen. Okay, so just keep that as a very simple system. The major histocompatibility complex MHC class 1 can recognize inside the foreign, the cell-to-cell interaction, and the class 2 can recognize the surface, or the one who are outside. So antigen presenting cells, I said that here, they are monocytes, macrophage, they're all dendritic cells, all of those are the same. Okay? So it depends on where they are. In the lungs, we call that alveolar macrophages. In the liver, it's Kupffer cells, and so on. Here you have a nice electron microscopy picture on the right. If you see here, that is a macrophage, an antigen presenting cells exposed to bacteria. You can recognize the bacteria here, and you see this dendritic part. They're going to catch the bacteria, engulf the bacteria, get the bacteria in, and then digest them. Those are Langerhans cells, the one we have on the skin. Okay, so I mentioned antibodies, obviously, but there is another system that is pretty close to be the same as antibodies. It's called immunoglobulins. They can serve pretty much the same function as antibodies, but they are just a different structure than antibodies. So IG for immunoglobulins. We have 5 different classes of immunoglobulin, and I'll tell you why it's important to understand them. IgG, IgE, IgM, IgG, and IgE. And then subclasses, there's dozens and dozens of them actually. If you're interested to just look at them, you can look at them on the textbook, the pathophysiology textbook that I would advise you to get if you can. Look at the syllabus for the reference of the textbook. It's called Essential of Pathophysiology. So those IgG are actually very important for the passive immunity. So what do we call passive immunity? That's another type of immunity. That's why I'm talking about this IgG now. We said innate immunity, acquired immunity, and to finish on the different type of immune response, I had to talk to you about the passive immunity. Passive immunity is what's happening between the mother. The best example is what's happening between the mother and a fetus or a baby during pregnancy. So if you look at the graph here at the bottom, it's a graph where we are talking about the curve here in bluish or greenish is the amount of IgG, or if you want, the amount of antibodies that the mother is able to give directly to the baby. And that's why we call that a passive immunity. It's a production from the mother directly to the baby. So the baby itself can't or is not producing those immunoglobulins. It's just receiving passively those immunoglobulins, and those immunoglobulins are going to serve as a defense mechanism. So during the pregnancy, you see the graph here at the bottom is birth time, okay, and then 2 months on and 5 months on. Before birth, during the pregnancy, there's a progressive increase of production of maternal IgG, maternal immunoglobulins, and slowly but surely over the months, and 8 months actually, of the 8 first months of the pregnancy, the mother is going to contribute slowly but surely to the immune system of the baby. But it's really during the last months or 3 weeks of the pregnancy that the mother is going to have a boost of those immunoglobulins, and there's a rush of those immunoglobulins to the baby to actually prepare for the labor and to prepare for the birth. Once the baby is born, actually, obviously, the contribution of the mother is going to drop. Okay, there's not much contribution of the mother. There's a drop here. You can still see that for up to 5 or 6 months, actually, there is something that the mother can still contribute to the IgG. But obviously, this is only through the breast milk. When the mother is breastfeeding, in the milk of the breastfeeding, there are a lot of IgGs, not really antibodies, but those IgGs. And if the baby is taking those IgGs, especially IgG and IgA, they will also be transmitted from the mother to the baby. If the mother is not breastfeeding, then obviously at that point there is no more passive immunity. At the point of birth here, there's no more passive immunity, and the contribution of the mother dropped to 0. You see, the baby needs some time. So if you look at this curve here, okay, the baby needs some time to have his own immunity build up. It takes around 6 months to a year, usually 6 months, for a baby to be able to build up his own immunity and his own immunoglobulins. That's why we usually advise mother to breastfeed for at least 6 months, to give the time of the baby to be able to produce his own immunoglobulins. So you get the idea. Okay, before birth, and especially the last 3 months, the last 3 weeks to a month of the pregnancy, the mother contribution is very important. And actually, this is the best immunoglobulin for the baby, because those are coming from the mother, and it's very likely that the baby who's going to be born from the mother is also going to live in the same environment as the mother, in the same country, in the same city or countryside, and exposed to the same bacteria, to the same viruses that the mother has been exposed to. So those are the perfect immunoglobulins coming from the mother for the baby. If you understand that, then what do you think can happen to premature babies? Babies that would be born before having the term of the pregnancy. Babies who would be born before the mother can have this boost of antibodies. And those babies don't receive the boost of immunoglobulins, and they may have a lot of different problems actually. But one of the most important problems for them will be that their immune system is going to be very weak, and especially if they're born very prematurely, they might actually need to stay at the hospital and become what we call bubble babies, the one we need to protect from infection bacteria as much as possible, because they didn't receive those immunoglobulins from the mother. So this is a very important part, especially for the first 6 months of life for a baby, is the passive immunity. Okay, that's pretty much the same thing I described before. Active immunity is the acquired immunity that I explain with the production of the memory B cells and so on, and the examples of vaccination and immunization. I just want to finish this lecture. It's been pretty intense, I know, pretty dense. So I hope you can pause if you need to. But I want to finish on this with the complement system. And I mentioned to you before, this is an important system, and it's kind of a complementary, obviously, to the rest of the system. So complementary to innate and acquired, complementary to the humoral and the cell-mediated. The complement system is made of proteins, and we're going to present the protein from C1 to C9. Okay, so 9 different types of proteins. So how does the complement system works? There is a activation phase. First, like almost any system in the immune system, you need to activate the system. How do you activate the complement system? There are 3 different types of pathways. The first one is called the classical pathway. Here, if you look at the graph, the classical pathway actually involves antibodies. And you see it's when a microbe, or here in that case a virus, will be recognized by antibodies, and they will activate the complement system. So you can see here right away that to be able to produce antibodies, you need the acquired system. You need B cells, you need plasma cells. So there's a link directly with the complement system. There are 2 other ways to activate the complement system. One is called the alternative pathway. If the microbe itself or the virus itself actually has something on this membrane or receptor on the membrane that can actually activate the complement system by itself, with no need of antibody or no need of a third player. And the third one is called the lectin pathway, and this is a specific sugar residue, a mannose binding lectin that can bind to a microbial antigen and be recognized by the complement system. But really, most of it is actually, I would say, for 80% or 90% of the cases, is the classical pathway that can activate the complement system. When we say activate, what does it mean to activate a protein? You can understand activating a cell. Activating a T cells or B cells is like activating all the enzymatic process, and the cells are going to start to look for the antigens, going to start to destroy. But for a protein, if you remember your chemistry, maybe there are 2 ways for a protein to be able to release energy. Either a protein can bind to another protein, and that creates energy, or, and that's the most common way, is actually going to split. Okay, so it's going to open up into different pieces, and by doing this, it's going to release energy. So that's the activation part, and that's the case for the complement system. C3. Okay, so here on the graph, C3 is the first of those complement proteins that are going to be activated by the 3 different pathways that I mentioned before. And C3 is going to split into 2. It's going to split into C3A and C3B. Okay, so 2 different pieces. C3A is going to have a double role. It's going to play the role of, it's going to help in vascular dilatation or vascular permeability and permeability. Vascular dilatation and permeability are key in the inflammatory process. We need that to activate actually and to help all of the cells we've talked about before to travel to the site of injury, for example. So I don't want to develop that too much. The vascularization, the vasodilatation, and the increase of permeability. We'll do that in our next lecture when we'll talk about the inflammatory system. But keep in mind that C3A is helping that. It's helping vascular dilatation, vasodilatation, and the increase of permeability of your vessels. It's also helping the chemotaxis. I don't know if you remember I talked about chemotaxis. Chemotaxis is the chemical. Okay, so chemo is chemical, and taxis like a taxi. When you're taking a taxi, is to go from one place to another. Okay, so it's a transportation system. It's the idea that you can move from one place to another. Okay, so chemotaxis means that you move by you chemically move. I don't know if I can translate that this way, but that's what it means. And it's actually the tracking system. When a cell wants to track a virus and follow the virus and kill it, he's going to follow a chemical footprint and is going to follow a chemical track that the virus is going to left behind when he's moving into your blood, for example. Okay, so that's what we call chemotaxis. It's this tracking system that neutrophils, macrophages, T cells, a lot of cells are going to use to track bacteria and viruses and to catch them. Yeah, so it's an important concept. So C3A will help chemotaxis, and we have vasodilatation. C3B is actually here on the other side. C3B is what we call a opsonin. An opsonin, I think I put that. Oh yeah, I'll put that here. It's called an opsonin. Okay, so C3b is called an opsonin. An opsonin is actually a protein that helps phagocytosis. It's going to help macrophages to engulf and do the phagocytosis. Okay, so just keep that in mind. An opsonin is a protein that helps phagocytosis. And C3b is also going to activate the second layer of the complement system, which is C5. And C5 is going to do like C3. To be able to activate C5, you actually split C5 into C5A and C5B. Yeah, my 5 looks like a B. So C5B. Okay, so C5A here help again for the vasodilatation and the increase of permeability, again, but because that's a very important step in the inflammatory system. And C5B actually is leading to the last step of the complement system. C5, you see here, C5b. C5b is going to combine with other proteins, C6 to C9. Okay, you don't need to remember the numbers, but by doing this, is going to form what we call the membrane attack complex. Okay, so the membrane attack complex is making holes, is going to attack the virus and really destroy the microbe at the end. There is a lysis of the microbe because of that. So that's why I was saying it's a very powerful system, because it acts on a very different level. If you consider C3b and C3a on the vasodilatation and permeability, help phagocytosis, also help the chemotaxis, all of those are very important steps for the immune system. And at the end, the C5 can also lead to the formation of the membrane attack complex, and at the end really lies the microbe. You see the various role of the complement system that is such an important system for the immune system and for the defense overall of the body. So I'm going to stop here for this lecture, and that was our second lecture for the immune system. I think by now you can tell that I'm kind of increasing the speed a little bit, and I'm also increasing the density of those lectures to after the first midterm that we had, and you had already a bunch of different systems that we covered, so that's why I kept the immune system. Now the immune system chapters is going to be the longest one we're going to have during the semester. So it's completely understandable that you can feel overwhelmed by it if it's the first time that you are hearing all of this. It's new concepts, it's new vocabulary. I completely understand that. So that's why I would really encourage you even more than before to contact me if you need to, and to work maybe in a group of students, find 2 or 3 other classmates, so you can study together, and make sure you don't wait the last minute before you start to study those lectures, because if you wait the 2 nights before the second midterm, there's no way you're going to be able to digest all of that. It's not difficult, but there's a lot of information to be able to understand. So let me know. Don't hesitate. I like to answer your questions. There is no useless question. Everything is important, and I want to be able to answer all of your questions. Don't hesitate also to ask your TA during the lab if you have any questions. And stay tuned for the next lecture. We'll talk about the inflammatory process mostly, and how inflammation and how all of the system we've talked about before is going to play a role against disease. Okay? Thank you.